So the title of this video was not clickbait. Dark matter is not a theory, and I think there's some confusion about that. So today I want to go over my top three, just my personal favorite evidences for dark matter.
Dark matter, do we need it? What is it? Where is it? How much? Do we need it? Do we need it? Do we need it? Do we need it?
The music I used in this video is the Dark Matter Rap by Professor David Weinberg from The Ohio State University, and I love it so much. I'm gonna link it below. Please go listen to the full version. I love it. It's perfect. Velocities. In 1930, Fritz Zwicky published a paper measuring the mass of the Coma cluster. The Coma cluster is a galaxy cluster, so a galaxy cluster will have 100 to like 1,000 gravitationally bound galaxies all orbiting around some giant Godzilla galaxy at the center. And he was using the Fourier theorem, which relates kinetic energy to potential energy, to measure the velocity in that system. So you can measure mass you can measure mass more than two ways, but you can measure mass using the mass to light ratio. So kind of just taking a picture and measuring the amount of light you get from each pixel and getting a mass. Or you can measure the velocities and use the Fourier theorem to go from kinetic energy to potential energy and make a mass estimate. And he found when he did that both ways, using velocities, there's like 400 times more mass than what he could see in light. And he published this and he called it dark matter, but in German, and everyone was kind of like, huh, okay. And the way I was taught this was that Fritz Zwicky made this measurement and then everyone ignored him for 40 years. And then Vera Rubin, of course, measures rotation curves in galaxies, and we'll talk about that in a second. And there's like this absence of anyone discussing this for 40 years, but I don't actually think that that's true. I read a lot of galactic dynamics papers when writing my thesis, and in the late 60s, people who were studying the dynamics of galaxies were like, well, maybe if we took our little disk and for some reason we just put it in a giant spherical potential, that would have an effect on the dynamics. And they would write about that, and it's like, that's just a dark matter halo. So obviously people were talking about dark matter halos. I really wish someone would like apply for a book deal and spend a year like researching this, just like reading all the galaxy dynamics papers in the 60s and 50s and figure out what the general attitude was, because I don't think people were ignoring Fritz Zwicky. I don't think that's what happened. But the general idea, as I understand it, is that, and then in 1970, Vera Rubin and her collaborator published this paper with this survey of galaxies where they're like, hey guys, there's lots of missing mass in galaxies as well. So in this case, she measured the velocities of galaxies like by looking at hydrogen gas. So like, you know, the spectra of hydrogen, and very accurately from that, using the Doppler effect, you can get a velocity because that spectra shifts. So she measured like in like radial bins the hydrogen lines and was able to plot like velocity versus radius. And if you do that same thing with the mass to light, you expect this plot. And if you do it with the spectra, you get this plot. So this is important because now we have missing mass at two scales. We have it in these giant clusters, and we also have it in all the galaxies we look at. I think here is where one of the confusions about dark matter like appears. When this is presented as like rotation curves, galaxies are evidence for dark matter, it's often presented with a single plot. And I think that might lead some people to think that this is like a systematic error. Like, okay, well, if you get the same measurement in every galaxy, then obviously something is wrong with the way we're taking the data or something. But it's not true that we get the same curve in every galaxy. Like, the amount of dark matter in a galaxy varies wildly. Like, some galaxies have really small light mass and they have a whole lot of dark mass. There have been galaxies observed without any dark matter. Well, very, very little dark matter at all. Some galaxies can be huge and have huge dark matter halos, and we can also learn about the shapes of dark matter halos by looking at hydrogen and measuring velocity of stars in that area. Like, we have learned a lot about dark matter, and it's not just this single plot. But in 1970, this publication was like, guys, this is real, this is happening, this is dark matter. It is not a theory. Dark matter is this measurement. Something is inside those galaxies that we observe indirectly, but we observe it. This is not a theory. Nobody made up the idea of dark matter. Zwicky and Rubin and collaborators, they didn't just decide, like, I'm gonna look for missing mass. They made a measurement, and they had an expected result, and they got an unexpected result. This is not a theory. It wasn't an idea. This is an observation. Dark matter is not a theory. It is an observation of missing mass.
Dark matter, do we need it? What is it? Where is it? How much? Do we need it? Do we need it? Do we need it?
Okay, number 2, dark matter is not a theory. It's a list of observations. The second observation is the WMAP data. Well, the WMAP data is from 2006-ish, and the Planck mission went after and was higher resolution. So this is from like 2012, I think. Evidence of dark matter. We did it. Look at it. She's gorgeous. And we'll move on to number 3. I'm just kidding. Has this ever happened to you? Has anyone ever shown you this exact plot and been like, evidence of dark matter? And it's like, babe, what is that? You can't post this picture and, oh, it's evidence of dark matter. What is it? Because, see, scientists do this thing. Scientists will look at data for 6 years. Just every day they go into their little office and they stare at the computer and they look at the same binary files for 6 full years. And over time, they develop a method, a way of plotting it that makes perfect sense to them. And they're like, oh, if you plot like Vx versus jy.r and you color code it by the normal vector, you get this beautiful plot. And it's like, I don't know what that means. You have to explain it to me. This does not scream dark matter is real. I've observed dark matter. It doesn't. So I'm gonna spend conservatively the next 26 minutes explaining this plot to you. I'll have to put my coffee down. Skip to this time step if you already know what this data means and you want to go to number 3. Okay. So in the beginning, you have the Big Bang. And if you're not into the Big Bang, this is also evidence for the Big Bang. So it's like a twofer. This is the free one. You're welcome. And the Big Bang creates your radiation, photons, your matter, and your dark energy, which I'm going to try not to talk very much about at all. And if we wanted to plot how those 3 products of the Big Bang change over time, we can make a plot like this. I'm going to put a little cartoon on my face. It's just a cartoon. Don't try to do math with it. I'm just going to draw it on like a tablet. On the y-axis, we can have like density or energy density. So how much of each thing is in like a cubic meter, if you want to measure it that way. It'd probably make more sense to do a sphere, but it doesn't matter. On the y-axis, we can have time, right? So after the Big Bang, time moves forward. Or you could plot temperature, right? Because the Big Bang's very, very, very hot. The space expands, temp goes down. So you could plot like temperature going down. Or you could plot like the volume of space, right? Space is very, very small, and then it expands, and volume goes up. Let's start with photons. What do you think photons do after the Big Bang? How does their density change with time, temperature, and volume of space? Imagine you have a box of photons right here, and you can just magically drop the walls. What do the photons do? They spread out, right? They fill the volume of the room. So over time, in your little cubic meter of space that you started with, the density of photons, of radiation in that volume is going to decrease by like r cubed, like the 3 cardinal coordinate dimensions. But also, photons, they're waves, right? So if they're moving along their direction of motion, they're going to get stretched, they're going to be redshifted. So you have to add like an extra dimension to that. So they'll go down by like, let's do temperature, T to the 4th. Okay, let's plot it on our plot. What about matter? Matter, you have your little box of matter, you drop the walls. What happens to the matter? It's also going to spread out with the 3 dimensions like are cubed, but it's not going to be redshifted because it's matter. So we can add that to our plot. It looks like this. And then we can talk about dark energy. I don't want to. Let's equate dark energy with the energy trapped in space. So as the volume of space increases, the energy density just hangs out. It's linear. The amount of energy in space can't change in space. Don't read too much into that. I don't want to do dark energy. It's fine. Okay, we plot that. There are 2 interesting points on this plot. I'll give you a second to see if you can point them out. Okay. The first is right around when this WMAP data was taken. It's where the radiation line crosses the matter line. Space started radiation dominated. The radiation was the dominant thing in space. And as space gets bigger, the radiation spreads out and space becomes matter dominated. That's the point where these 2 cross. The second interesting point on this plot would be where the universe goes from being matter dominated to dark energy dominated. Fun fact, we're currently right here. So we live in a dark energy dominated universe, which is why people talk a lot about how the rate of expansion is increasing and things are moving in the heat death or the cold death or the crunch. And just fun fact, new existential dread just dropped. So I wanted to use that little cartoon to set up where and when and what the universe was like when this plot was taken. This plot was taken right about the time that we went from living in a radiation, well, we weren't there. This was before stars. This is when the universe goes from being radiation dominated to matter dominated. I need you to picture this early universe. It's very, very hot. The photons are just vibing. They're dominating the universe. What does this mean for matter? First, baryons. The Big Bang makes like a bunch of baryons, like 75% hydrogen, 24.9 whatever helium, and then a little bit of lithium. By the way, Big Bang nucleosynthesis, like that observation is also evidence for dark matter, but I'm not going into it today because it's not my favorite. So what happens to our little hydrogen and our little helium guys when they are living in a very hot radiation dominated universe? They become ionized. Strip their electrons away, they are vibing. They are positively charged nucleuses of hydrogen and helium. And because of that, all of those baryons, they're ionized, they're charged, they're coupled to the photons. The electromagnetic force is having a party, and you just have this oopy-goopy plasma. The radiation is just pulling the baryons wherever it's going. Dark matter, however, if we know a thing about dark matter, right, it's that it's dark. It doesn't care about the electromagnetic force. So while this oopy-goopy plasma is happening with our ions, the dark matter is just like gravity. Little overdensities of dark matter start sucking other dark matter toward it. It can't pull the baryons because the baryons are up in that plasma. Like, yes, they can feel gravity, but that's not what's important in our hot, early universe, right? We're forming these little overdensities, these little seeds of dark matter halos. That alone is evidence for dark matter, right? The fact that galaxies exist is evidence that in the early universe, the little seeds of dark matter halos started forming. Imagine there was no dark matter, okay? Your oopy-goopy plasma, I'm gonna stop saying that. The plasma, the radiation and baryon plasma is just stuck together. They're moving, they're coupled, and then eventually space gets big enough, it cools down enough that the ions can like pull in an electron and like settle down and start flooping together to form like big masses. If there's no dark matter, those molecules and atoms that are now like pulling away from the radiation don't have these little halo seeds to fall into, right? They have to start forming their own like baryon galaxies. And that kind of delays the process. It delays the formation, hierarchical structure formation of dark matter halos. We need something for the baryons to fall into. We need like the little masses to already be there, or galaxies don't exist 10 billion years later. I mean, they might. They would just be really small, and they'd be farther apart. Okay? The way our universe looks right now requires dark matter to be there just after the Big Bang. But we haven't gotten to this plot yet. But that's the picture. You know where the plot is taken. You know what's happening when we look at this plot, right? There's your plasma with your ions trapped to your radiation, and your dark matter is forming these little halos. So I am now going to show you some awesome visualizations from Professor Adam Hincks. I'm going to link his website below, and I'm going to try to say his name multiple times to give him accurate credit for these awesome visualizations. I think this is okay, right? I can just show you his website. I feel like it would be much weirder if I just stole his idea for these visualizations and then made my own and then was like, look at this awesome plot I made. So I'm just going to show you his. And if you want to go check out his website, I will link it below. So on the top left, you're going to look at the distribution of mass over a radius of the dark matter, the baryons, and the photons. And on the right, you are going to see where they are plotted. Imagine it's t=0. It's the Big Bang's happening. All of this stuff is stacked together. And I'm going to move this ticker a little bit forward in time so you can see what happens to these three things. Okay, notice the center of this plot is very blue. Because, right, dark matter is just like following gravity. It's just sinking together, it's sticking together. But you also see this yellow ring, which is the combination of the red baryons and the green photons being coupled and moving away from that mass together. Yay, see, the same thing is still happening. So our dark matter, you're getting a nice little dark matter's halo seed, and you still have this yellow ring where baryons and photons are coupled. Now I'm gonna move to the time step where our WMAP photo is taken. Photo, yeah, it's a photo. Okay, sorry. So I've moved to the redshift where that WMAP photo was taken. And what you see is that ring looking a little bit more green because the photons have started to like uncouple and cool down, and at the center you still have this dark matter halo. So this is where the photo was taken. Remember what this looks like, and I'll move the thing up forward a little bit more. Okay, so here we are at a much later redshift. You see the inside of your density is like purpley now because red and blue make purple. The baryons are sinking in. You see the green photons are moving out to larger radii. Okay, this is starting to form a galaxy. So this is what happens. That ring that you see is called a baryon acoustic oscillation because it kind of looks like a sound wave, right? You have like your bang and then everything's moving outward in like a ripple. But the definition of that ripple is going to depend on the mass of your dark matter that's in the center of that oscillation, the mass of your baryons that are like trapped with the photons and kind of starting to pull away at the time when this image is taken. That is going to define the shape of your baryon acoustic oscillation. And this is how we make this WMAP data. Let me show you with another beautiful, just 10 out of 10 visualization from Professor Hincks from the University of Toronto. Here's his website. I'll link it below. Okay, so what you're looking at is one of those rings, a single baryon acoustic oscillation, but you are only looking at the photons, which is why this whole thing is green, because photons are the only thing we can observe, right? We don't observe dark matter, and we don't observe baryons directly either, right? We observe the photons that they give off. So what you're looking at is photons. This is a single like shell of that ripple leaving the Big Bang. The brightness of the shell is going to be dependent upon the number of photons in that area that we see. So this plot is a representation of what's happening in Big Bang cosmology, but it is not showing the whole universe. What this is a slice of a single overdensity region in space moving outward and expanding with space, right? Like if you did actually have a little box of photons and you remove the walls, they wouldn't expand as like a ring, they would expand as like a shell. So you were looking at a two-dimensional slice of a 3D object. And I also want to talk about the size of this object. This does not represent the whole universe. This is 150 megaparsecs, which is about the size of a dark matter halo of a galaxy. It's not a coincidence that that happened. And there wasn't just one. There's a bunch of galaxies, actually. So each of these shells will move on to become a galaxy. Those overdensities are necessary to form structure. I'm not going to say this word again. Don't make fun of me. Stop it. So now I'm once again going to use the wonderful visualizations of Professor Hincks from the University of Toronto. He's linked below to show you how you go from this to this. Okay, we're going to slowly increase the number of shells. They're going to be slightly different sizes depending on the distance or depending on what the slice of our 3D object is like. They're going to interfere with each other and change what we see if they're overlapping, all that good stuff. So we can keep increasing it. And oh my goodness, it's starting to look very interesting. It's starting to look like the WMAP data. What? So when somebody plops this plot up and they're like, look, it's evidence of dark matter, what they're talking about is the direct observations of the photons in these baryon acoustic oscillations, which are representative of dark matter existing at the center of these shells and pulling baryons down. This image is an indirect observation of dark matter, because if dark matter was not there in the early days of the universe, we would not see these shells. This would not look like this. There has to be dark matter. Another thing people like to do is show you this and say, look, dark matter is real. And then they do Fourier analysis on this plot and show you this power spectrum, and they say, even more proof, dark matter is real. I usually like to set things at like high school level and then kind of explain and build on that and hope that people follow along. But I can't do Fourier analysis. It would take me months and months of researching and figuring out like a really nice way to explain it. And then I would spend, 18 hours, an 18-hour video on Fourier analysis, and like 6 of those hours would be about like the random girlfriend of a mathematician, and no one wants to watch that. I have a full-time job. This is just for fun. This is like a hobby. So I'm not going to teach you Fourier analysis. I am going to like do some hand wavy. It's kind of like this, and hope you follow along. But I'm sorry. Again, if you just want to skip to number 3, it's here. So imagine you're at a playground and someone is pushing a child on a swing and you're standing here. And you're doing the thing where like you pretend they're going to hit you in the face, and then you're like, ooh, and they never hit you in the face, okay? If you plotted like the X position and the Z position versus time of that kid, it would look like this. But maybe instead you wanted to look into frequency space. Like instead of looking at where they were in physical space, you looked at the frequency of the swing. So like how often it almost hits you in the face, like a per second rate. If you did Fourier analysis on this plot, you would get a power spectrum that looks like this, where on the x-axis, just a list of frequencies, and on the y-axis, the amplitude, the power. And it would have like a single peak. And that single peak is the frequency of when that kid is almost hitting you in the face, right? And because it's a swing, if you could figure that out. It's like a pendulum, right? You could figure out the frequency and you could test your plot, but it doesn't matter. Now, let's say you want to get like the average frequency because you want to compare it to this equation or something. So you do this 10 times where somebody drops the kid and you take the data. Except one of the times, the kid does that little butt wiggle. So now he's going like still up and forward, but also side to side. And when you do the Fourier analysis of that plot, even though it kind of looks similar because you're not measuring y, you don't have information that he's going side to side in your Cartesian coordinate plot. If you took the Fourier analysis of that plot, it looks like this. Now it's a little bit different. It's a little bit different from your initial frequency. So you can look at all your frequency plots and right away you see which one that kid did that little butt wiggle, right? Because you have two peaks. The big peak is like his forward motion, and this little peak is like the frequency of that side movement that had an effect on this plot. So if you want to do analysis of like a physical thing that happened, you can look in frequency space and you can get a different set of information. Well, I mean, it's the same information. It's a different way of doing analysis. Okay, that's what Fourier transforms are. There's lots of math and calculus and spherical harmonics, but this is the gist, okay? Okay, so you take this plot, you do like your Fourier transform real good, and you get this plot. So on the y-axis, it is a power spectrum of temperature, again, like the amplitude of our oscillations, and they put like an angular distribution. It's fine. It's a similar idea to our swing plot. And each of these peaks can tell us a bunch of information. Remember how the kid does a little butt wiggle, like the physical situation of the problem changed, and it appeared as an oscillation we could observe. Each of these peaks shows us something interesting about the physical situation at the time when the universe was going from radiation dominated to matter dominated, and that can tell us about the constituents of our universe. Just a note, the green on this plot is like theory, and the red on this plot is observations. Dark matter is not a theory. Dark matter is a list of observations. Okay? So some of the, I'm gonna go through the peaks of importance until we get to dark matter. The first peak, the biggest peak, the most important peak, because its amplitude is biggest, tells us that space is flat. I don't want to get into it too much, but just imagine you have your sound wave moving out. The shape of that wave would depend very strongly on the shape of the thing it is waving through, right? So if you have a universe that looks like this, you would definitely be able to observe it in this plot. So from this information, you learn that space is flat. That's not what this is about, who cares? The second peak gives us information about the amount of baryons in the universe. Remember, in our baryon acoustic oscillations, baryons are the primary player. They're doing the oscillating, right? They're going from the photons to the dark matter, flooping up and down. Okay, so this tells us the overall density of baryons in the early universe. And this actually leads to a big problem in physics right now that like nobody talks about as much as dark matter, but it's the missing baryons problem. Some people call them dark baryons, but that's confusing. Okay, so these are baryons, traditional baryons interacting with radiation baryons. But when we look all over the universe and we look at stars where most baryons are, a bunch of them we can't find them. The baryons are missing. I am dropping a bigger problem than dark matter in the middle of this video that no one seems to talk about, the missing baryons. It's fine. They're baryons, they interact with radiation, they behave like baryons, but where did they go? What a mystery. The third peak, however, tells us the importance of dark matter. Because again, they're oscillations. You have your baryons oscillating between the photons and the dark matter. The amount of dark matter is going to affect the oscillation, right? If you have a whole big giant glob of dark matter, it's going to oscillate a lot more strongly than it would if you just had a little teeny guy, right? Because like then, yeah, here's a plot to show that. So from this curve, we can put like a number on how much dark matter there is. And that's why you'll see a little pie chart that's like the universe is 27% dark matter. That is where this number comes from. We observe indirectly, but we observe that the universe is 27% dark matter. It is not a theory, it's an observation. You guys hate when I repeat stuff, but it's important. So, it's not a theory. Dark matter is a list of observables. We see it in velocity. Now you understand why we see it here in this plot and here in this plot. Tell your friends.
Dark matter, do we need it? What is it? Where is it? How much? Do we need it? Do we need it? Do we need it? Do we need it?
So my personal most impressive evidence from dark matter is like not a controversial pick. It's the most cinched it evidence of dark matter. Whatever the sports term would be, this is the big one. It's the bullet cluster. This image. Again, it's an image. It's not a theory. It's not an idea. It's something we observe. Here it is. Here's dark matter. It's right there. So it's called the bullet cluster because it looks like a bullet. The bullet cluster is a result of the collision of two clusters of galaxies. So 47 minutes ago or whatever, when I was like, Fritz Zwicky was measuring dark matter in 1930 in the Coma cluster, I said a galaxy cluster is like 100 to like 1,000 galaxies. They're real big boys. They're gravitationally bound. They're surrounded by dark matter. They're big hunks of things. And occasionally, two of these guys, two giant galaxy clusters, will collide. So let's talk about what happens when two galaxy clusters hit each other. Well, we can split them up into components, right? The dark matter is collisionless, or it's very, very, very almost collisionless. The cross-section might just be very small. It depends on what dark matter actually ends up being. Surprise, we don't know. So your galaxy clusters hit, the dark matter just goes straight through each other. Like, it's like nothing happened. Okay. The galaxies are made up of stars and gas and dust and some other stuff. Stars, they're also collisionless. Go right through each other. I can tell you why stars are collisionless, even though they're made up of matter. It's just because they're very far apart. If you took the sun and the closest star to it, Proxima Centauri, and you shrunk them down to the size of a ping pong ball, the distance between them would be like 800 miles. I'm in Boston. What's 800 miles away? Like Florida? I don't know. Imagine trying to shoot a ping pong ball from Florida to Boston and hitting it. You would never do that. Like, there's no, like, I mean, you could. Technically, you could do it. But if you're just throwing them together, they're not going to hit. So in our two galaxy cluster collisions, the stars will also just, I mean, obviously their orbits will be impacted. They'll fly off, but they're not going to like directly collide, create a big explosion for us to see. But galaxies also have gas, right? So the gas inside these galaxies, the gas in like the medium, the intergalactic medium between the different galaxies in the cluster is going to slam into each other, and it is going to stop and collide and produce a bunch of photons. We'll see it. X-rays, huge. Like, we'll see it. It will light up the sky. Well, I mean, for our telescopes, not for our eyes. You can measure the results of a galaxy cluster collision. You would see lots and lots of X-rays from the center, like the site of the collision where gas and dust is colliding, emitting lots and lots of photons. And if you could measure the mass, you would see that since most of the mass is trapped in dark matter, it just kind of moved through. So you would see your bright center with X-rays and then just two big blobs of mass on either side, because the dark matter is all the mass, the vast majority of the mass in those systems. And that's exactly what we see with the bullet cluster. This is from like 2004, I think. So the center, the pink, is the X-rays, and the blue is all the dark matter. Well, we can't observe dark matter directly, right? So how did we see it here? It's with gravitational lensing. If you have a big, giant mass, it will bend space-time and cause light to curve around it. So you can see the curved light and you can infer the mass. Gravitational lensing by itself is evidence for dark matter because we use it to look at dark matter indirectly. Here we use gravitational lensing to show that the result of a collision between galaxy clusters is proof of dark matter. If dark matter did not exist, you would not see this. Again, we're measuring it indirectly, but it is there. This is not a theory. This is not an idea someone came up with. We observe it. We see it. It is an observation that we see. And before you're like, well, how do we know? There's another one. Another bullet cluster. It happens again. Dark matter is everywhere. We see it, we observe it. Dark matter is not a theory, it's a list of observations.
Dark matter, do we need it? What is it? Where is it? How much do we need it?
So I did this little video about string theory, and I was like, it's not really a theory because it doesn't offer observations. And in the comments, a lot of people were throwing dark matter into the same pile, which confused me. Because I'm so sorry to say this again, but dark matter is not a theory. Dark matter is a list of observations. It is nothing like string theory. Again, I mean, I'm on the defense of string theory now all the time. String theory is trying to answer questions that we get from observing things, whereas dark matter is a thing we observe that raises questions and requires theories to explain. So of course there are theories of dark matter, tons and tons and tons and tons of them is dark matter. A particle, is it a superfluid? Is it Newton's law of gravity depending on r? It's like r squared plus a little epsilon or something, and who knows? Lots and lots of theories. Don't get mad at me, but none of them have yet been very successful. But that doesn't mean we have not learned anything about dark matter since 1970. I mean, this is like 2012, this is 2004. Like, we are making progress with theories of dark matter. Theories of dark matter to explain dark matter. But dark matter itself is not a theory. It is a list of observations. I'm so sorry. I'll stop, I promise.
Dark matter, do we need it? What is it? Where is it? How much do we need it? Do we need it? Do we need it?
If you're one of these people in the comments of that video who want us to throw away dark matter, what you're suggesting is like we kind of just stop looking at space because we see it. Like, it's there. There's evidence of it everywhere we look at multiple scales in cosmology, in astrophysics. Like, the dark matter is there. We can't just ignore it. We can't just stop looking at it. Like, we can't throw out dark matter. It's not a theory. It's in our universe. It's how our universe works. And if your suggestion is like, well, all your measurements are wrong, like there's a systematic human error or something, like what the kids write in lab reports, like, I hate to say it, but that's also a theory of dark matter. Your theory is just that all physicists are liars or all physicists are stupid, both of which are wild to me. If you actually think every single physicist is lying and or wrong and stupid, I propose a challenge. It's not a challenge in that I want you to communicate with me what you're doing. Don't do that. This is for you. This is like your own personal gold star. I want you to measure dark matter. So Vera Rubin had a very fancy for 1970 telescope, and she measured the rotation curves of galaxies. But we have the software and the ability to just do it with nearly any telescope. So if you actually, like 100% think that dark matter is not real, my challenge is that you measure it yourself. This amateur astronomer, Geheniau, I think based on his website, he's like an audio-visual like software designer, and he built a radio telescope in his backyard, and it works remotely. He's got like some software that he uses to take data. He took data of the Milky Way, he measured the rotation curve, and it looks like this. He found the dark matter in the Milky Way. You can do this at home. Like, if you really 100% with your whole chest and heart believe that every astronomer, every physicist, every cosmologist is a phony or an idiot, you should measure it yourself. I mean, yeah, this is going to take some time. Like, probably a couple $100 to build the telescope, probably a year of testing it and figuring out like what you're measuring and how it works, and then a while taking data. But it's pretty achievable. It's an achievable goal to measure the dark matter in the Milky Way by measuring the rotation curve. Do it. Did I mention that dark matter is not a theory? It's just the list of observations. And like, you can't just throw away dark matter. You can't just do that. That would be like if you kept digging up the dinosaur bones and you were like, throw away the theory of dinosaurs. We'll never see a dinosaur. Throw it away. Although I realize that like comparison falls apart because like you at least see the bones. What are the bones of dark matter?
Dark matter, do we need it? What is it? Where is it? How much? Do we need it? Do we need it? Do we need it? Do we need it? Dark matter, do we need it? What is it? Where is it? How much? Do we need it? Do we need it? Do we need it? Do we need it?
So I really liked Job's telescope data. I thought it was so cool. You might have noticed I called him an amateur astronomer. And I feel like amateur, at least the first time I heard someone call someone an amateur astronomer, I was like, well, that's kind of rude, because amateur is one of those words with two definitions, right? On the one hand, it means like whatever you're doing doesn't look professional, which would be an insult. On the other hand, an amateur is like a lover of something, someone who does something just for the pure joy and fun. And that's what an amateur astronomer is. Amateur astronomers are the best astronomers. They know the night sky better than any astrophysicist ever will because like they look at it all the time. In 2016, I went camping overnight so that I could be at a spot where I could see the eclipse the next day. And there were a bunch of amateur astronomers there, and they all brought their telescopes the night before. They're setting them up, and like they're just so lovely. They want everyone to learn about space, and it's amazing. By the way, there is a solar eclipse in 2024, and if you didn't watch the one in 2016, try to go somewhere to watch it in 2024. I mean, you probably only need to see it once, but it's really cool. On my crackpot video, I don't think I said enough that you can be someone who's not a professional scientist, who's like super into science, and also not be a crackpot. Like just not having a degree does not make you a crackpot, and I would never want people to think that. So I made a little compass, you know, the crackpot compass. And so on the x-axis, you have like education level going all the way up to PhD. And on the y-axis, you have like crackpot to scientist, okay? So the bottom left is a crackpot, like someone who doesn't understand the field they're trying to work in, but is also not trying to do that. And they're not doing any science. Crackpot. I've done a video on that. And then the top right, the boring, just people who work as scientists. And you also don't have to have a PhD to be a professional scientist. Like if you get a bachelor's degree in like biochemistry and you go work at a company and you're doing like bench work, you're definitely still a scientist. Like I also didn't mean to imply that like, oh, look at the PhD. No, that's terrible and stupid. Absolutely not. Is someone who has the education, they can understand the field, but they choose to sell crystals for quantum healing instead, you know, like a grifter. But the top left is the new one I'm introducing today. It is the amateur scientist. Someone who does it for the love of it. Like your amateur astronomers. I was coming up with a list and the next one that popped into my head was like ham radio people. But ham radio is just astronomy, right? It's the same thing. It's awesome. Ham radio people are awesome and very cool. But it's also just astronomy. It's the same as an amateur astronomer. But then I thought of my favorite example, which is gardeners. You know, like imagine you move from California to North Carolina and you want a garden. Are you going to call a botanist? Are you going to buy a botany book? No. You're going to go to the library, to the gardening club, and there are going to be some amazing people who have been gardening in North Carolina for 26 years. They're going to give you starters. They're going to tell you whether or not you can grow a lemon tree or a peach tree. Like scientists. For the love of it, and that's beautiful, and that exists, and that's real, and I hope you didn't think I thought otherwise. Okay, bye.
Dark matter, do we need it? What is it? Where is it? How much? Do we need it? Do we need it? Do we need it? Do we